Hi everyone, I'm Shuang Hu from Joynext China. I'm glad to present our recent work, live streaming object detection by leveraging GPU with AVA platform on EVAOL on this virtual symposium. First of all, let me give a brief introduction of Joynext. We are a Chinese Tier 1, mainly providing IVI and V2X products for global OEMs. We are also a multi-member of SOAFEE Special Interest Group to contribute in the developing of software-defined vehicle. I'm from Advanced Engineering Department of Joynext, which focuses on the state-of-the-art technologies such as SOAFEE. The motivations of this work are to verify the complete process of applying SOAFEE reference implementations, including both software and hardware components. Also to verify whether GPU can be used in AVA platform with EVAOL. We will perform live streaming object detection as an example use case in this work. Here is our software architecture for both cloud and edge sites. In the cloud, we use Amazon EC2 G5G instance, which is powered by AWS Graviton 2 processors based on ARM architecture, and also NVIDIA T4G Tensor Core GPU. In the edge side, we use AVA platform, which also has ARM-based CPU, and we manually plug in NVIDIA GPU GeForce RTX 3080 Ti. Therefore, the cloud and the edge sides have the parity environment. Both run OS on ARM-based CPU and the NVIDIA GPU. We will build container images in the cloud first, and then push them to the Docker Hub manually to make sure we run the same containers in both sides, so the results should be the same as well. Here are mainly two containers, RTSP server and the YOLO object detector. RTSP server receives live streams from video files or camera inputs and provides APIs for publishing live streams. The other container, YOLO object detectors, receives live streams from RTSP server and performs object detections on each frame, then saves the object detection results to files or send the results through WebRTC. Let's further look at the detailed architecture for the edge side. To simulate a more real scenario, the camera input is more preferred than just video files. However, we found that EVAOL running in AVA platform cannot support the camera input. Alternatively, we run RTSP server container in Raspberry Pi with the camera capturing the raw video on a display, and then run YOLO object detection container in AVA platform with NVIDIA GPU RTX 3080 Ti. The results of live streaming object detection can be viewed on the browser of another PC with WebRTC. To use NVIDIA GPU on Docker on EVAOL, we should first install NVIDIA GPU driver on EVAOL. Here, we build EVAOL with GPU driver in the beginning. To run AI models, we use NGC containers, which are pre-installed with CUDA toolkit and support most popular AI frameworks. This is our final hardware setup for the edge side. Now let's watch the record videos for demonstration. First, we will perform the object detection on the video file in the cloud side. Let's watch the video. Here is the basic information of the AWS machine in the cloud side. Its OS and GPU information. Then let's see our Docker file. which is based on PyTorch, WebRTC, and other required components. Then let's build the image with Docker. Since we built and pushed it before, so almost all are cached and it's quick. Okay, now next let's run the demo. First, we need to start the RTSP server to read the video file. Okay, it's finished. Then let's run the YOLO container with GPU to perform the object detection. Okay, now you can see the numbers, which means the object detection results on each frame. And now it's running. Well, okay, it's finished now. Then we can check the output video, which stores the object detections results. Okay, besides in the cloud side, we also perform the same object detection on the same video file in the edge side. And let's watch the video, and we still run the exact same commands. And here is the basic information of our AVA platform. Still, we will start the RTSP server first. And then run the YOLO container to perform object detection. Yeah, here comes the results. Okay, it's finished. Yeah, we can, let's see, we can still check the output video. Yeah, it's there, and later we can watch the results. Okay, so here is the object detect results from both cloud and edge sides. Let's see the comparison. And we can see that the accuracy of object detection are the same on each frame. But we notice that the FPS from the cloud side is higher than the edge side. For the cloud side, we can have 24 FPS around, but in the edge side, we just got 15 FPS around. Also, we can easily and quickly modify the YOLO v5 models in the container, and then we can pull and update the container image on our edge side. So here is the results from different YOLO v5 models. And the above is the results from YOLO v5N, and the below is from YOLO v5L. Yeah, we can see the comparisons. Firstly, we noticed that the above results from EuroV5 model, which has a higher FPS around 15, and the below just have a lower FPS slightly. And for the accuracy of object detection, we noticed that in the below image, we can see the model detects the traffic light successfully, but the above model fails to detect the same traffic light. So we can see that if we have a more accuracy model, of course we lose the FPS somehow. Yeah, that's it, the comparison between different EuroV5 models. For this demo video, we will perform object detection with live camera inputs in the edge side. First, we are in the AVA platform to check the OS and GPU information. Then we will start the EuroV5 and the WebRTC server in AVA platform. Then we switch to the Raspberry Pi, and it's the OS information for Raspberry Pi. And then we will run the RTSP server in Raspberry Pi to process the live camera inputs. Okay, now it's running. Then we can see the results of the live streaming object detection on the browser through WebRTC in real time. Yeah, it's just like this. And the right part compares the object detection results from video files and the camera ports. And the above one is from the video file, and the below one is from the camera inputs. We noticed that the FPS from the video file is higher than the camera, but we have the same object detection results on each frame. Okay, these are all the recorded videos for demonstration. Now it comes to the conclusions. In this work, we verified the whole process of cloud-native development and the deployment way using SOAFEE reference implementations. We also successfully performed the live streaming object detection by leveraging GPU in AVA platform. During this work, we also met several issues, such as the current version of EVAOL for AVA platform doesn't support the camera device. Instead, we have to connect the camera to the Raspberry Pi. And besides, we found that the container image, which includes PyTorch and the CUDA toolkit, is too big to build and deploy. And I think in the future work, we are going to fix those issues. Okay, in the end, thanks for watching. Bye-bye.